All right. So, yeah, I'm happy to introduce Russell Coleman. It's been really great working with him for the last couple of years. Before the paper that he's going to talk about today, he was actually a part of our some of our work on Bayesian Rex, which was one of our learning reward function from demonstration algorithms. And he'll be talking about sort of a cool new way of doing something at least vaguely similar in spirit. So yeah, Russell, go for it.
Well, thank you so much. Yeah, and thank you all for being here today. I'm very excited to talk about this. So if you have not seen it yet, my thesis is titled A Transformer-Based Approach to Inverse Reinforcement Learning, which as we go on, you will see that is a very straightforward title of what's happening.
Russell, quick question. Are you using
yes.
a wireless headset or something? It could be a wireless headset.
I am not using a wireless headset. Is it an audio issue still?
Yeah, it's getting pretty garbled.
Yeah.
Oh, Lord.
I'm having to do Bayesian inference to infer what you're saying.
Oh, my God. Yeah, it would. The problem is my phone doesn't let me join simultaneously.
You should be able to call in.
Yeah, that's a great idea. I might try calling in.
Yeah, that's a good idea.
Let me, wait, where do I find the number for that?
That's a good question.
At the bottom of the screen, there should be something that says like invite new people. And one of the options on there will be like copy to clipboard. And then you can paste that into anywhere and there will be a phone number.
Or in where it says where there's a microphone, if you click on the up arrow, there's a button which says switch to phone audio and it'll tell you what you need to do.
Oh, perfect. Thank you very much. I appreciate this.
Fancy.
Okay, excellent. Yeah, sorry for the confusion, and I hope this will be cleared up in just a second. Okay. I did a test just a few seconds ago, and it unfortunately was not reflected then. That would have been helpful. Okay, can everyone hear me through this?
So far, so good.
Hello?
Yes,
oh,
so far,
excellent.
so good.
I'm very glad to hear that. Okay, thank you. All right, so back to the presentation. First, I'm going to start with a little bit of background. I'm going to talk about the problems of reinforcement learning and inverse reinforcement learning, for those who are unfamiliar, as well as some related work in the field and sort of how ours compares to that. Then I'm going to get into our algorithm. I'm going to talk about our method, as well as two things that are key to making it work, including transformer models, as well as a concept called the aligned reward polytope, which came out of a paper called value alignment verification out of this same lab recently, which is very helpful. And then go into results. We're going to evaluate it on a few different environments, and then talk about how it can be extended in the future. So for background, I'm going to talk about reinforcement learning. And in order to understand that, we need to begin with a Markov decision process, because this is what we're going to use to sort of frame everything I'm talking about today. So in the Markov decision process, or the MDP, there's an agent. And this agent can be you, it can be a video game character you're controlling, it can be a robot, it's anything that can be in a state and take actions to change its state. And so in this example here, agent is in state 1 of all of these 6 states, and there are different actions it can take to move around. And when it does that, it can get a reward. So you can see here, moving from state 1 to state 2 has a reward of +3. state 1 to state 6 has a reward of -1. And these actions need not be deterministic, but for the sake of this, we're going to sort of assume that they are. Like when you take one action, you're guaranteed to be in another state. So you can see that the agent, if it wants to get the most reward, it shouldn't just head directly to state 2 and get the +3. It should instead get the +1 by going down, and then a +4 by going to state 5. And so what we've just done by finding the way for the agent to get the maximum reward is solving for what's called a policy, which is a mapping from states to actions. And that is essentially what the problem of reinforcement learning is. You're trying to, given your state, figure out what action you should take to maximize your reward. And your expected reward is this expression all the way on the right, which is just your reward at each state with some potential discount factor, which just means maybe you don't care about actions in the future as much as actions closer by. So this is all well and good, but when formulating these MDPs, you can sometimes encounter issues, especially when you're modeling complex and real-world problems. And in particular with the reward function, it can lead to very unexpected things. So let's say like you've got a robot that you're training to keep your cat's litter box clean, and you reward it at the end of each day if there's no litter in the box. One optimal solution to that is to kill the cat, because then it's always going to be clean, right? It solved the MDP, but it's clearly not done what you want. So setting this reward function for a lot of real-world things can be problematic. So a great way to sort of get around this is to learn from demonstration, right? This is what humans do. You watch someone perform the action, you understand what they're trying to do, and then you replicate it yourself. So an easy way to do that, and an area that there's been a lot of research in, is something called behavior cloning. And this is sort of the most direct approach to that. And what you do is you just learn this mapping directly and put aside the reward function for now. So you have these demonstration trajectories, and the trajectory is just sort of a video of the agent doing what it's doing. And you just watch what the agent does in each action, and you train a network to mimic that. But this has a few issues. Number one is that as soon as you get into a state you haven't seen, you're completely out of luck. And you might not be able to figure out how to get back to a place you do know, right? You get compounding error. Once you start to go off, who knows what's going to happen. And additionally, you can only match the performance of the demonstrator, right? You're trying to just imitate exactly what these trajectories are, but you can never do any better, right? You're stuck with whatever that is. One good thing though, it's very fast. I mean, this is a very straightforward way of doing it. But one thing that we really want to do for a lot of cases, I mean, each problem is different. But if we recover the reward function from the trajectories instead of just learning that mapping, then what we can do is apply reinforcement learning on the MDP with our reward function to be able to train the agent to achieve the action independently. And so if it's, for example, the agent while it's learning, if it goes to some area of the state space that is not in any of the demonstration trajectories, that's fine because it still has this reward function, so it can still figure out what it needs to do. In that way, it's sort of a lot more flexible, and you also get just sort of this additional piece of information. And so this is sort of the area of research we're going to be going into today. And this is inverse reinforcement learning because we are recovering that reward function as opposed to using it to get the trajectories. All right, so traditional methods for this IRL, the inverse reinforcement learning, is to come up with some estimate for our reward function at the beginning. And then you loop. So you take that reward function estimate you have, use it to find a policy, which again is just reinforcement learning. Take this policy, run it a couple times and see what it does, and compare what those policy rollouts are against your demonstrations, against what you started with. And then you apply some algorithm to update the estimate of your reward to make your policy's trajectories more like the demonstration trajectories. And you just repeat that until your policies are close enough to being like the demonstrations. And then at the end of this, you have your reward function. You're all good. And you can use that to do reinforcement learning. Again, get as many policies, you've done it. There are a few issues here though. Number one is that in the inner loop, we have this RL step here. And the problem is that that is expensive. Reinforcement learning is not very sample efficient. And this is going to require a lot of steps. And it's in the inner loop, right? This is happening many, many times. And so for a complicated problem with a complicated reward function, this might not be possible to do. It might just take too much time. Another problem is that we have the same issue as behavioral cloning, which is that we're just trying to make our trajectories exactly match the demonstrations. We're assuming they're optimal. And I've hit on this point a few times. I'm going to discuss it in a second about why it's really so important. So one piece of related work to solve this is an approach called T-Rex, which came out of the Perl lab a couple of years ago. And so the way this operates is by taking the input trajectories and training a network to predict from trajectory to some reward estimate. And then what you do is you get rankings over all your trajectories. You say, I might not know what the reward function is, but I can tell you that this trajectory is better than that one, and this one is better than that one, and so on. You have the network predict all of these values. And then for any pair where you have a ranking, you just train it to say, like, if this one is predicted to have a higher reward than the one that we actually know to have a higher ranking, we penalize the network. And you keep iterating until it's able to accurately rank the trajectories. And so then you can just use this forward pass through the network to be able to get an estimate for your reward. And this has a lot of benefits. Number one is that it does not require optimal demonstrations anymore. And this paper actually finds that if you use this method, you can outperform the demonstrator when you train an agent on the resulting reward function. But it has a few issues. Number one is that you actually need this additional data to be fed into the network. Additionally, each time you want to get a reward estimate when you're training your RL, it requires a forward pass through this to be able to see, from whatever state to what is my reward. So now I want to go back to what I was saying a second ago about the issue of why I've been talking about the optimality of demonstration so much, because what we really want to do in the very long term of this is to be able to get like a robot to watch a human perform something and be able to replicate that. But human demonstrations tend to be non-optimal. And there are many reasons for that. There might be something that requires too much skill or precision. Like maybe you want to press a button within a millisecond of some event. Humans can't do that. Moving a boulder or a box, that is just impossible. You might not get that. Additionally, if you've ever watched someone try to explain things to a toddler, they often exaggerate their behavior in order to make it more clear what they're trying to show. But in doing so, that exaggeration is another form of suboptimality. So in any of these cases, maybe you just can't do it, or maybe you're not trying to do it because you want to be more clear. We still want to be able to uncover that underlying reward. And that's a hard problem, but formally, we're going from this mapping of these trajectories to some reward function with the key distinction that these trajectories are attempting to convey the same reward function. And so I'm using attempting to convey loosely because that just means, they're not necessarily optimal. They could be, but they could not be. But the key thing is that there is some pattern that our network is able to deduce from this. So in order to actually perform this mapping, we use a transformer. So a lot of y'all may be familiar with this because this is something that's been very common in natural language processing, like GPT-3 and BERT and all these famous networks are all transformers. The key benefit of this type of network is that it's excellent at sequences. It does sequence-to-sequence modeling, and it's very good at modeling relationships inside of its input data. Importantly, it's been finding a lot of use outside of the natural language processing field in recent years for these reasons. And so what we're hoping is that this transformer model will be able to, seeing these input trajectories, which are sequences, which is absolutely perfect for this type of network architecture, that it can model the relationships, even long-term dependencies between things, like if the agent takes an action early on that affects something later, we want the network to be able to reason about that, and transformers are perfect for this. So once we feed the data through the network, we then have the problem of how to actually represent the reward function that that we're predicting. So if you've read a lot of IRL literature, you may be familiar with a very common thing to do is to assume a reward function is linear. And this seems like a really restricting thing, but it actually turns out not to be. You can do this without loss of generalization, because the way you do this is you take each state and represent it as some feature vector, and the reward is only linear from that feature vector, like within the parameters of the feature vector. And there can be an arbitrary nonlinearity that generates those feature vectors, so you can really represent any reward you want. And also something to note is that we are fixing all of the rewards to the unit sphere. And the reason for that is that if you train an agent with one reward or that same reward, but everything's doubled, it's going to exhibit the same behavior. So for simplicity, we're just capping the norm of everything at 1. So what you get is that all the agent needs to do, or sorry, all the network needs to do from its input trajectory is predict some point on the unit sphere that it thinks represents the reward.
Very quick question.
So just some overview. Yes?
When you say, what do you mean by R is linear? Linear in what?
Linear in the reward, or sorry, linear in the feature vectors.
Got it. Okay, thanks.
So each state will have its associated features, and then it's linear in the features. Yeah, so thank you. That is a good clarification. All right. So a quick overview of the method before we continue. We are going to be using supervised learning with a transformer to try and learn this mapping of trajectories to reward weights directly. And this gives us a few key advantages, in that we relax the optimal demonstration requirement, like T-Rex, and we get a very quick pipeline. It requires this data up front with all of our trajectories annotated with reward functions. But once you've trained the network, you can then show it any agent operating in the environment, and it should be able to get that reward function that the agent is expressing in a single forward pass. It's really great. And one thing to note as well is that in all of these things, I've been showing the input as a reward set of the various trajectories. But all the results we're presenting are actually in the single shot case. The network works just as well if you give it as many trajectories as you want. But we found it did well enough in the single shot case that's what we decided to focus on. So one other thing that is an interesting point about this mapping is that, and this is an issue in IRL more generally, is that uncovering a reward function is an ill-posed problem. So for example, in this environment that we have a little agent with a orange triangle and a blue square. And if the agent decides to move to the right towards the blue square, it could be that the agent just loves that it loves squares. It could be that it hates triangles. It could be that it loves blue. It could be that it just likes going to the right. All of these are appropriate reward functions to explain the behavior. And so in the case of a very complicated environment with maybe many possible correct reward functions, we don't want to confuse the network by penalizing it for an incorrect a prediction that's different from the expected value, but is actually also correct, right? If its reward function is able to explain the behavior, then we're all good. We don't want to penalize it for that. And so what we're going to do is borrow something from the value alignment verification paper called the aligned reward polytope. And so the way this works is that essentially when we're watching the agent act out some policy, we can learn what the possible reward features are that could represent that policy. So in this example here, in this grid world, we have these 6 little squares, and the top left square is sort of the end. Once the agent reaches that, it's over. And you can see that no matter where the agent starts, so in each square, we have the action that the agent takes. The agent's going to make its way back to the top left and end. If it starts in the white squares, it will go and avoid the gray square. When it starts in the gray square, it'll just go directly and end. So if you think about what could be driving that agent behavior, what is its reward function? We can see that the agent does not want to sort of prolong its life. It's trying to just get to the end as fast as it can. And we see that beyond that, it cares more about avoiding the gray square than ending the trajectory quickly. And so what you get if you actually go and do the math, if you assume that the reward features for this are how much time it's spending on the white squares and the gray squares, we get a 2-dimensional reward space. And for each action it takes, you can actually split the space in half into by saying that only this half of the reward space could be the reason that the agent took that action. So this other half is not possible. And when you do this for all of the possible actions, you'll get an intersection of a lot of half spaces that will form this polytope shape, which you can see on in the diagram on the right. So this cross-shaded area is the area that represents all of the possible reward functions for this grid world environment that could accurately explain the behavior. So if our network predicts something anywhere in that region, it's made a good guess, and so we don't want to penalize it. And if it's predicted anywhere else, we just want to move it towards that aligned reward polytope, which is the set of all these reward functions that can explain the behavior. However close we can do that. All right, so on the right here, I have a diagram showing a reward feature space from one of the actual environments that has a 3-dimensional reward. And so the green dot is the ground truth reward that we're training it to predict. And because it's a little hard to show this in 3 dimensions, I've just drawn the outline of the aligned reward polytope in red, where it intersects with the unit sphere. And then yellow is the centroid of that. And so again, when we have the network do this forward pass from trajectories to reward, it's predicting some dot along the sphere. And so then what we do in order to actually do the backprop and update the network and train it, our loss is the sort of just the fastest direction to get to the polytope, to this little red outline. So it need not be the green thing itself, the ground truth reward. It just has to be anywhere in this shape. And we also experiment, we're going to see some results on this later, with trying to train to the centroid of the polytope instead of just anywhere within it. And that's the yellow dot. And the reason for that is it sort of canonicalizes the reward function in that anywhere within this space of all of the reward functions that explain the behavior, anywhere within it, we now have this sort of one dot that represents this as centrally as we can. And it sort of provides a more consistent reward signal to the network. It's always aiming right here, and there's no ambiguity. So later we'll test the performance of that. So in order to actually do this evaluation, we started with a grid world environment. And in which the agent is a square centrally located. It can move up, down, left, right. There are 3 different square colors, and it has a certain affinity for each color. If that affinity is high, it wants to spend time near those squares. If it's low, it wants to get as far away from it as possible. And importantly, it can also eat the squares. If it steps directly on top of it, it gets a reward of some multiple of the affinity. And so what we can do is watch the agent act and then try and predict its affinities for the different squares. We would love to be able to watch humans do that, but there are a couple of problems with that. Mainly that it's just very time consuming to do, and it's harder to replicate. So what we opted to do is to train reinforcement learning agents, and we did that using the PPO algorithm. So in our data set, we want to have something that can approximate human suboptimality, because in the end, this is for human demonstrations. So what we did is we stopped the training early. And so the agent, if you watch in this video, this is one of the actual pieces of data from the training set for the global environment. It's going to do a couple of behaviors that don't really make sense, wiggle sometimes, generally do things that aren't perfect. And we're doing this in order to, again, approximate that maybe a human will press the wrong button sometimes. You know, it's going to get things wrong, and see how the network performs with these demonstrations. All right. So this is the graph showing various networks training performance in classifying rewards for the grid world environment. And what I mean by classifying is that to make it a little bit easier to see the accuracy, we just ask it if each box is positive, neutral, or negative. We're going to get into the regression problem in a second. But what we see here is that the transformer network performs great as we expected. It beats the sort of baseline networks that I made to sort of test more traditional methods. We've got the just a standard multi-layer perceptron network performs the lowest, followed by a convolutional network, and the transformer beats them both. But one thing that's very interesting about the transformer's performance is that it was actually able to beat me. So I have a human baseline right around 90% there, which consisted of me sitting down, watching a ton of these videos, and trying to predict what I thought was the reward function. And the transformer was able to get about 4% on me, which we're very excited about. And we think that some of the reason for that might be that there are a lot of times where the agent has sort of quirky behaviors in different like suboptimal areas. Like maybe, you know, the network that loves all the green boxes might wiggle in some certain situation, and the transformer might be able to pick up on that better than me, you know, as a human watching only so many. But it's an encouraging result. And another thing to note here is that if you look at the slightly faded lines up top, that's the training accuracy. And I included that just because of a little cool thing I thought, which is that all of the networks sort of overfit on the training set the same way. They were each able to get very high accuracy on it, but the transformer just shines in generalization performance. All right. So now I'm moving on from the classification to the more traditional problem we've been talking about this whole time, where we're actually predicting a reward on the unit sphere. So this is a little bit harder to show the results, but so what we decided to do is for each of the networks trained, there are 3 below. One where the network was trained to predict just whatever the ground truth is, one where it's trained to predict the centroid of the ARP, and one where it's just trained to head towards the ARP however it can. We take those networks, have them predict some rewards, train agents to maximize those rewards, get some rollout trajectories. We let those agents act, and then we check how well those agents did under our original reward. And so what we find out, and this is for the grid world environment again, is that these agents actually perform remarkably well. They all performed very, very close to the ground truth reward. And I think part of the explanation for that is if you look at these distance to ARP bars, those show us the average distance from the network's predictions to this ARP, which again is all of the rewards that could explain whatever behavior we're trying to go for. They all got extremely close. That is the bar on the right. They're all like around 0.06 distance from the ARP, which is very, very small. Interestingly, the one that performed the best on the distance to ARP metric is the one trying to predict the centroid. I suspect that it is because it has that stronger and more consistent reward signal. And since it's trying to predict the middle, even a small perturbation will still keep it within the ARP. So it'll be generally better, it'll get more zeros. But what's interesting is that the one trying to predict the distance to the ARP directly actually performed worse on that task it's trained to do than the one that predicts the centroid. But we can't just stay in grid world. We're looking at a couple different environments. We have 3 more, Space Invaders, and then 2 complicated environments based on the OpenAI ProcGen set of environments. We took 2, Dodgeball and Miner. Interestingly though, most RL environments that exist in the world are made really for one specific reward function, because that's how most papers expect them to operate, and mostly you're just testing RL methods on them. But we in this want more of like a real world thing where there are many different things that can optimize. So we had to modify the environment slightly. On Space Invaders, I added different ship types. In Dodgeball, I added more opponents of different types that can behave differently, and you can attack them differently. And you again have to predict your affinity for different agents. And in Miner, we added new types of gems, changed boulder behavior in such a way that changing the reward function will noticeably change the agent in order to test our method. All right. So there's good news and bad news in terms of how it performs on these different environments. The good news is that it performs very well in Space Invaders, just like it does in Grid World. But we noticed some struggling in Dodgeball and Miner. And so there are a few reasons we think this is. And notably, it still performs better than random, just not great. Number one is that these environments are highly complex in a few different ways. First is that the observations are pixels on a pretty huge grid, all things considered. So it might just be hard to actually learn good features from that. But additionally, we found that in the step of getting the data, it's hard to get a high quality training set in these, just because each agent takes so long to train that even when training it for longer than the Grid World and Space Invaders, the agent's behavior was still highly erratic and did a lot of things that I couldn't figure out just from watching it. And so maybe this will be solved if we get humans to demonstrate this, and that would be a good thing for future work. Additionally, we want to investigate more varied types of environments, because even though we had these 4 different ones, a lot of them sort of have the same operating principle, and that there are different types of agents, and we're sort of trying to predict how much our agent has preference for these other things in the environment. But there are plenty of other ways you can sort of create multi-objective settings, and we'd like to try some more varied ones. Additionally, in the more varied environments, we would like to find some that have ambiguous rewards, which seems sort of counter to this goal. But what that will do is create a much larger ARP, which will sort of allow us to better differentiate between the network performance, because in these, they were all mostly, they all performed great, at least, in Grid World and Space Invaders, but they also all performed similarly. So we're thinking that that will give us a much different result, and it could be interesting to investigate. Additionally, really getting to the bottom of Dodgeball and Miner, I'm personally think that it's a thing that it's hard to get a high quality training set right now. Maybe that's solved by just training more, or maybe the environments are just not suited. But we'll investigate that. And then another thing is for all the regression problems, I used, I think it was 30 samples along the unit sphere for rewards, trained agents on each of those, and then generated 100,000 trajectories in total to use as the training data. But it's possible that that's, too much, and we want to see like how low can we push it, how minimal can this training set be, while the network is still able to perform well in the environments that it does do well on. That'd be an interesting thing to look at. Anyway, thank you all for listening to my presentation. In the end here, I just wanted to shout out for all the help and support, especially from Dr. Scott Neekum, Jordan Schneider, and Daniel Brown, who are all in the Perl lab, and were amazing throughout this entire process and helped me so much. And also to everyone on the committee who is here today to listen to me through this presentation, and all my thesis readers like Dr. Biswas and Dr. Chatterjee. And with that, the presentation is over, so I will go into questions.
Thanks, Russell. Yeah, so questions. I guess we can start with the committee members.
Cool, very fascinating work. So something which I would love to get your input on is, so you use transformers to great effect in this work. I did not have a good baseline of like, if you went using transformers, what else would you use, and what is this particular key enabling technology bringing to the table which other approaches would not do very well with?
Oh, that is a great question. So we did try a couple different types of networks, like just the multi-layer perceptron, which is sort of the complete low baseline, and some CNNs. But I think really the reason the transformer performs so well and the reason we picked it is just its ability to model relationships between data and the input sequence, especially given that what we're looking at when we're looking at these trajectories is a series of states over time that might have long-term dependencies. And so the whole mechanism of self-attention is really well suited for that. And that's why I think it was able to outperform the human. I don't know, does that answer the question?
I mean, I think in general, that's always the reason why I use transformer models. But I mean, I'm curious to know if you've seen any scenarios which or any evidence to support that is actually what's happening. Like this is the reason why it's actually doing well, or is it just what I'm trying to get at is like the reason why it's working so well. Is it because of the things that we expected to be working well for, or is it just because that's more complicated network? So in that case, maybe an MLP with more layers and more width would also work well.
Oh, I see what you're saying. Okay, yeah, that is a great question. I think in order to get to the bottom of that, we definitely require some sort of forensics and actually like looking at the different layers of the network. I think that's a bit of an open problem as to why it works the way it is. I do know there's some great transformer visualization tools that I've used that let you actually like see what relationships it's modeling. I actually took that's what this was from. This was a Python program I ran. That's a great idea. I might try and just run this on our transformer and sort of see how it's operating and what relationships it's forming.
Yeah, that would be fun to see. Yeah.
Mm-hmm.
I guess the other thing I would add is that without, or the MLP would not allow for variable length inputs, and RNNs are just hot garbage.
Okay. I mean, but that to some degree, right? But then there's like cheap hacks that you can do off there, which you can like take like the longest sequence length that you can have, and you can always zero patch as needed. So
yeah,
yeah, but like the longer the sequence gets, the more you forget things, and yeah. So one thing which hasn't been brought up and we have no evidence for, but might be true, is that seeing it as a sequence rather than like a bunch of states that we're mapping rewards from individually is that you're sort of like avoiding a failure of what's the phrase? You're not double counting rewards by seeing two good correlated things in the same in subsequent states and like getting, you know, too high or too low value or reward out of those states, right? Credit assignment. There we go.
So well-calibrated credit assignment.
Yeah, and we have no evidence to believe this is true, but it would be cool if it were.
Yeah. I mean, I think that raises like questions of like investigating why this is working so well. That's cool. Yeah.
Okay,
so another
you
question
guys
that
are completely. Go ahead, Jaideep.
No, please go ahead. I can come back.
Okay, I was going to say you guys have completely lost me, so I kind of want to pull back a little bit. And Russell, for a non-specialist like me, and I think you have members of your family who are probably non-specialists as well. This is your thesis. This is your honors thesis. So what is the thesis or hypothesis that you were setting out to demonstrate in this work? And were you able to, you know, what was the conclusion? Thesis was true, thesis was false, something more complicated. To step back from the, you know, the very detailed work, which is excellent work, but I just want to sort of ask that meta question.
That is a great question. And so I think the central thing we were trying to test is if it's possible to do this mapping on the screen just from trajectories to reward in a supervised, you know, with traditional supervised learning techniques and actually get anything meaningful out of that. And so I think what we found is that it's sort of environment dependent. I mean, we need to do a little bit more digging and see what exactly is causing that. But it can be successful and it can beat human, the human baseline if you have the right environment. So I would say I think we showed that it is definitely possible to do this and get a supervised mapping from these trajectories to rewards with just a single forward pass. I don't know, does that answer the question?
Said you're muted.
Oh,
I'm
sorry,
muted?
I was. Yeah, I was. No, I was. Yeah, so sorry. Yeah, that was my only question. Thank you, Russell. Jaideep, you can go ahead, ask your other questions, or Scott, or any.
Cool. So your feature functions that you're using over which the reward is defined as a linear combination of those, the feature functions seem to me like it would be like a representation space over the trajectories, right? But they're representations which are relevant for predicting rewards. It's kind of like coming up with like a basis set. Can you talk a little bit more about how you learned those?
Oh, that is a great question. Yeah, the feature, like designing a good feature space is definitely an open problem. Wait, I guess I can't figure out where that slide is. That's fine. I think I kind of felt okay making that assumption that it's linear and sort of pushing that off, because that's a very common thing to do in a lot of similar papers, like this assumption of a linear reward from the feature space. But I will say that in a lot of environments, there might be like a sort of obvious way to handcraft it. In each of these, we did end up handcrafting the feature space. But it is also possible to generate feature spaces sort of automatically if you're looking for like a hands-off approach where you're not really kind of giving it that boost of the human creating the feature space. I actually did some work on that in the BREX paper where we created this system that's able to sort of self-supervise learn a feature space by watching a ton of, you know, rollouts that have the states and actions and do things that just sort of kind of predict on its own input. So like we'll give it a couple of states and an action and ask it to predict what the next state is. We'll give it two actions and two states separated by an action and ask it to predict what action was in between them. We'll give it two states and ask it to predict how long is in between them. And by creating all sorts of little losses like this, you can train a network that is able to sort of encode information about the states into whatever encoding space you need in a way that actually does contain meaningful information. And so it is possible to sort of generate this feature space automatically. There can be some issues with that, like it can doesn't always work. You know, it works for some things better than others. But I think that's definitely an open area of research. But I will say for this paper, what we did is to just sort of create a feature space for each environment that made sense with what we knew. And the specifics of what each of those feature spaces are is included in the paper itself. You can see the exact way all of that is calculated. And it's also, I'm going to post the link to the code on the GitHub if you're more curious. But so does that answer the question?
Yeah, I think so. That's good. Thanks. Although, if any of you, Russell, Scott, or Jordan, if you're interested in discussing more how we could use contrastive loss functions to do representation learning on that, I think that would be rather interesting. I feel like it should be possible. Like you should be able to.
Well, the really challenging thing is just that you need something that's going to be able to represent reward linearly. So like even with like all the auxiliary tasks that like Russell was talking about that we used in our other paper, like even if you can predict all those things linearly, that doesn't necessarily mean rewards predictable linearly. Like it could be based on some of the same underlying features or relationships, but it could be a cubed relationship instead of a squared relationship or something. And like, then you can't do it linearly from the features you had. So I think that's the really tricky part. If you were doing like arbitrarily, if it could be nonlinear, then yeah, I think it would be easier to maybe use a contrastive method or something like that. But
In that
I also
case,
think it's like,
but maybe I didn't fully understand then the necessity of the linear. It sounded like you're just doing linear because it's simple, but if that didn't seem to me.
No, all that half space stuff doesn't work unless it's linear.
Okay, so that's actually the bigger reason to use the linear functions.
I think another advantage of the linear function is it just gives us an easier way to, like an easier output for the network. Is just we need to predict X number of weights and then we're done. I mean, I guess you could do that with a nonlinear way actually too, but I feel like this is very, it seems the most straightforward.
Okay, cool. Sounds good. I don't have any more questions.
I just have one question. So, Russell, for scaling this to humans, it seems hard because it's much harder to get data from people than from, just like agents you trained up or whatever. So, what all do you think it would take to scale this to humans?
That's an interesting question. I was just thinking about that. I mean, I think one of the potential things that could use more investigation in this is just, the amount of data set or the amount of data we use is very high, and that's definitely poses a challenge for collecting data from humans, right? And so I think knowing how notoriously data hungry transformers are, that does pose an issue. But I mean, there are lots of, I think, advances in supervised learning techniques that might sort of give insight into maybe ways we can augment the data or fiddle around with it more and see if we can still create a working network from a sort of minimally small net or data set. But at least off the top of my head, I think that really is the main obstacle. I don't think there would be a lot of other issues beyond just volume of data, because we are just doing the mapping, from any amount of any trajectories, no matter what kind of suboptimality they have to the reward function. So even if the humans behave a little strangely, I think it should still be able to learn that. I would be very optimistic. I would love to see a more full-scale test of that. I was not able to sort of do that in the time allotted, because that would have I'd had to sit down for countless hours just playing Grid World, and I was like, I don't, I don't know if I can do that to myself. But yeah, I would love to see that.
So when collecting human data, how would you get the ground truth reward functions from people?
Oh, I see what you're saying. Yeah, I mean that is a little bit of an interesting problem. I think the way I would go about doing it is just putting some people like giving them some written reward with some way to like map that written reward to these weights. It's definitely a little challenging because I think if you give people feature weights directly, they might not be able to interpret that.
Yeah.
I feel like if we're like, I don't know, really think it through, I feel like there must be a way to sort of convey these feature weights in a way that humans will understand and be able to attempt to reproduce. I don't know. What do you think on that?
Yeah, I mean, I think we would have to have like a set of feature weights that we knew corresponded to some task that could be described in language or something like that. But yeah, it's tricky. I think that's the sticking point that we've thought about the longest and not really known a good solution to.
Yeah, I'd be curious to see some sort of like if there would be a way to do like just like apply NLP methods to that. Although that seems like a whole rabbit hole that might not go anywhere. I don't know. Yeah, that's definitely an area that needs future investigation. But I think once the data can be collected, we're all good. It's just collecting that data is very, very challenging.
Yeah. Other questions? Anyone from the audience?
So Russell, what's next? Where are you going next? Or what you doing next?
In terms of the research, or in terms of personally?
Are you going to grad school or company or taking a break?
I am going to company immediately after graduation, but I would love to return and continue research at some point in the future. I was just thinking I'd take a break from school for a second, maybe come back in 1 or 2 years is what I would like to do.
Sounds good.
There are also 2 questions in the chat. So one was, what's the intuition of the unit sphere for rewards? So why are they restricted to a sphere?
Oh, I see that. Good question, Vincent. So the reason that they are a sphere is just that if you have the agent try and optimize, let's say just some reward function, and you train another agent to optimize that same reward function with all the weights doubled, they're going to exhibit the same behavior. So there's sort of no reason to have this extra degree of freedom that doesn't mean anything. So we normalize all of the reward weights to 1, or sorry, the norm of the reward weights to 1 to keep everything consistent. So, we're always predicting in the same little region. And then I do see the other question from Sarah. Thank you for the question. Regarding the human baseline, 90% seems kind of high. In terms of comparative literature values, I don't think I can give a number for that because I don't think, I haven't seen a similar sort of classification type baseline for this before. I did it because I thought it would be a good way to sort of like intuitively show the network performance. But I think the reason it's as high as it is for 90% is, I mean, I was really trying my best watching these, and I was very familiar with the environment and at least how I would behave in the environment. And so I think I did pretty well. But I mean, again, it's not too hard of a problem for a human where you're just watching the square interact with its environment. And if it seems to favor certain types of squares, okay, maybe I can conclude that it likes those squares. And so I will say for a completely random classification thing, it would be at 33% in this, if that's a good comparison. How much do I think would be vary among different people or more complex systems? That's a good question. I actually did have one other person give a human baseline. I sort of drafted my cousin for like 2 hours, and he scored actually very similar to me. I think he got like a like an 88. So I would say I think it's definitely a very reasonable value, at least for the grid world environment. Okay, and then I see a question from Alan saying, is the output prediction of the transformer a set of weights that represent a linear function, or the results of applying that linear reward function to the input? Yeah, so that you're right that is the reward itself. The output prediction of the transformer is the set of weights, and so you dot product that set of weights with whatever the feature space is, and then that gives you the reward function. So yeah, it is the first thing you said. It is the set of weights. I hope that answers it. Awesome. Okay.
All right. Anything else?